came with his first balloon. The Rosier Quisterland floated above Paris for 23 amazing minutes. This first human ascent was made with a hot air balloon. Early experimenters thought some virtue in smoke made it possible for it to fly, and their reasoning led them to trap an airtight bag of paper or silk in an attempt to cause the bag to ascend. It was not until later that experimenters realized that hot air and not smoke made the balloon rise. Hot air is lighter than the same volume of cold air, and through the operation of the principle discovered by Archimedes in 232 BC, a balloon filled with hot air is capable of rising from the ground a considerable burden. The balloon continues to rise until the weight of the balloon and the air it contains is equal to the weight of the air it displaces. In some balloons of this type, fire was carried aloft on a platform suspended below the bag to replenish the supply of hot air. In any case, as the air in the balloon begins to cool, it loses buoyancy and settles back to Earth. In 1766, the English scientist Henry Cavendish had demonstrated the properties of the gas hydrogen, which is only about 1/15 as heavy as air. First successful ascent in a balloon filled with scent. For 100 years, hydrogen was used as the lifting gas during the development of lighter-than-air craft. Although the use of hydrogen was less dangerous than carrying a fire aloft to produce hot air, its nature made its use extremely hazardous. But early aeronauts went ahead with great courage, achieving remarkable records for distance and altitude, despite the fact that their fragile craft were completely at the mercy of the winds. The first successful dirigible or steerable balloon was flown by Henri Giffard on September 23, 1852, using a steam engine for propulsion. The development of dirigible balloons was slow during the next 45 years until 1898, when the Brazilian aeronaut Alberto Santos-Dumont made the first gasoline-powered flight at Paris. Other experimenters followed his lead, among them the German Count Ferdinand von Zeppelin, who completed the first dirigible with a rigid framework in 1900. In 1911, Zeppelin began the operation of the first commercial airline, carrying passengers between two German cities. During the war, which began in 1914, Germany put the Zeppelin to military use in bombing raids. England and the United States, although they had successfully operated small dirigibles, limited lighter-than-air construction mostly to non-rigid captive balloons anchored to the ground by steel cables. These sausage balloons, more properly called kite balloons, were employed in observation service in the front lines for spotting artillery fire and for observing enemy troop movements. Following English, the United States in 1916 began making a number of blimps or small non-rigid dirigibles for military use. It was in a Navy blimp that helium gas was first successfully used as a lifting aid in 1921. As it is non-inflammable and almost as light as hydrogen, helium was immediately adopted by the United States for use in all subsequent Army and Navy lighter-than-air craft. Our monopoly of this important gas is of great strategic importance, and it has eliminated the fire hazard to American airships. The long-distance possibilities of a type of rigid dirigible were brought to the attention of the American public when the British R-34 arrived over Long Island after a transatlantic voyage. While the R-34 drifted over the landing field, an officer descended by parachute to instruct the ground crew in the unfamiliar technique of hauling down the big airship. As we were to discover years, the handling of big did art difficult to master. In 1923, the United States Navy launched an American-made dirigible, the ZR-1, at Lakehurst and christened it the Shenandoah. A crew of American Navy men with German advisors took over its operation, and the Shenandoah completed 2 years of service. Encountering a storm over Ohio, the aluminum alloy framework of the airship proved unequal to the strain of conflicting air currents, which destroyed the Shenandoah. A more successful record is that of the ZR-3, completed in 1924 at the Zeppelin plant at Friedrichshafen, Germany, for the United States. Under command of Dr. Hugo Eckener, the ZR-3 took off from Germany for a transatlantic flight non-stop to the Naval Air Station at Lakehurst, New Jersey. In 80 hours and 45 minutes, the ZR-3 completed her historic crossing. Navy officials accepted the ZR-3 at Lakehurst and named her the Los Angeles. Of all the large United States dirigibles, the Los Angeles is the only one to enter active service by honorable retirement. Modern commercial use of the dirigible began with the German Graf Zeppelin, which crossed the Atlantic with 20 passengers in October 1928. Dr. Hugo Eckener, veteran airship commander, was in charge of the many subsequent flights of the Graf Zeppelin, which carried hundreds of passengers across both North and South Atlantic. In the autumn of 1929, the huge dirigible undertook a flight around the world, completing the long journey in a few hours more than 21 days. The United States Navy designed and built two gigantic dirigibles which embodied a number of improvements in design. The first of these ships, the Akron, went into commission in 1931. Among the innovations found in this airship were a new truction and provisions for carrying 5 scouting planes. Early in 1933, the Akron's sister ship, the Macon, made her maiden flight. Both of these great American dirigibles were destroyed by accidents at sea, but the casualties were very low because the use of helium as a lifting gas prevented explosion and fire. On March 4th, 1936, the great German Zeppelin Hindenburg was launched. By the use of oil-fed diesel engines, her designers avoided adding the fire risk of gasoline to the known hazard of more than 7 million cubic feet of hydrogen gas. The Hindenburg certainly merited the name airliner, for she had every conceivable provision for the comfort of her passengers. But the gas bags of the Hindenburg were filled with hydrogen. 10 successful passenger crossings of the Atlantic were completed in 1936. On May 6, 1937, as Hindenburg reached Lakehurst after that year's first crossing, a mysterious explosion destroyed the great ship of the air. Roaring flames of hydrogen, the twisted skeleton of the giant airship in which 36 passengers met death. These tragic symbols marked the end, at least for a time, of lighter-than-air transportation. Many experts believe, however, that the airship has certain advantages which will someday assure its place in aerial transportation. Only time can tell what will be the fate of the Ridge airship, which has been called man's boldest engineering experiment. The first living creature to fly existed millions of years ago, a flying reptile, the pterodactyl. In time, reptilian scales evolved into feathers, and eventually came the development of the bird, which is the inspiration for man's efforts toward true flight. The first man-made device that rose into the air was the kite, which reached a high degree of perfection in China many centuries before the beginning of our civilization. In the 15th century, the magnificent artistic and mechanical genius of Leonardo da Vinci produced the designs for several flying machines. A model built from one of da Vinci's designs is part of the unrivaled aeronautical collection in our National Museum. But the first heavier-than-air device actually to rise in free flight was entirely different in design and appearance. It was a toy helicopter made with feathers. Sir George Cayley of England was one of the first to advocate the study of heavier-than-air craft as a means for solving the mystery of true flight. The flying machine which Cayley designed was a helicopter, a boat-like device with steam-driven propellers mounted vertically to lift the machine from the ground. Following Cayley's lead, William Samuel Hansen in 1840 tried to finance the building of aircraft intended to connect the various parts of the British Empire. Hansen's design called for a monoplane with a wingspan of 150 feet, powered by a 30-horsepower steam engine. After Henson became discouraged, his partner John Stringfellow built a model plane which in 1848 flew a distance of 120 feet. This was the first successful demonstration of the principles of dynamic flight. In Australia, Lawrence Hargrave made an important contribution to aircraft design with the development of improved stability in the box kite. In 1889, Pithancourt of Paris devised an ornithopter, or bird-winged flying machine, which flew by flapping its wings up and down. In the United States, a patent was granted in 1889 to the maker of this weird model. Needless to say, the machine didn't work. The experimenters who most advanced the art of flight during this period were those who experimented with gliders of sufficient size to enable them to coast on the air. This glider, constructed by Otto Lilienthal of Germany in 1894, completed more than 2,000 successful glides. It is demonstrated here by Paul Edward Garber, in charge of the aeronautical collection of the United States National Museum. Lilienthal's gliders were controlled by shifting the weight of the operator's body. The end of the 19th century saw the successful gliding experiments of Octave Chanute, a distinguished American engineer. Chanute produced in his designs a new factor of stability and devised control surfaces for steering the glider. Chanute was also responsible for the introduction of truss construction, which provides increased strength. The first large power-driven model airplane was flown on May 6, 1896. Built by the American scientist Samuel Pierpont Langley, this was number 5 in a series of machines which he called aerodromes. Powered by steam, this model flew 3,200 feet above the Potomac River. Based upon this design, Langley built a full-sized man-carrying aerodrome under a War Department appropriation. 1903 brought the official test of the big aerodrome, and the test brought disaster. Discouraged, Langley ceased experimentation, but the same aerodrome was reconstructed and successfully flown by Glenn Curtiss in 1914. Nine days after Dr. Langley's disastrous experiment came the first controlled human flight. On December 17, 1903, at Kitty Hawk, Wilbur and Orville Wright took off for the first sustained flights. Continuing the successful gliding experiment in Lilienthal, the Wright brothers had built and flown efficient gliders, and it was experience gained in glider construction that aided them in developing the first successful airplane. In the Wright airplane, the elevators were placed in front of the main structure on outriggers, while the rudder was similarly mounted on outriggers behind. Instead of ailerons, which were a later development, the Wright brothers employed wires and pulleys for twisting the tips of the wings to tilt the ship from side to side in flight. The plane was launched from a monorail by means of a rope and falling weight. And now, having reached the moment of man's first flight, let us see what it is that keeps an airplane in the air. The lifting element of an airplane is called the wing. The outline shape of the wing determines its flight characteristics. Let us consider the wing immersed in air. The airplane wing is set at a small angle to the fuselage, which angle is called the angle of incidence. The angle of attack of the wing will vary as the airplane takes off, climbs, maneuvers, and descends. A propeller starts the airplane moving through the air. Now, it must be understood that air is a fluid, somewhat like water, but less dense, and being a fluid, it cannot be separated like a solid, but moves around any object immersed in it. The air striking the lower surface of the wing is slowed down and deflected downward, and as a result, we have a force tending to push the wing upward in the opposite direction. Let us now consider the action of the wind on the upper surface of the wing. You will note that the shape of the upper surface is such that the air following its contour has farther to go than the air following the contour of the lower surface. The air traversing the upper surface must therefore move at a higher velocity than the air following the contour of the lower in order to arrive at the trailing edge at the same time. Then, since an increase in velocity of a liquid or a gas results in a decreased pressure against the surface along which it is flowing, it follows that the pressure of the air on the upper surface of the wing is less than the pressure against the lower. Thus, we have a difference in pressure, which is the force tending to lift the wing. Measurements show that the upper surface contributes about 2/3 of this force, while the lower contributes 1/3. Every wing has drag caused by its shape and the friction between the air and the wing surface. The force of the propeller counteracts the drag, and the lift counteracts the weight of the airplane. Now, with the main element explained, that of the wing and how it lifts, the other great factor of flight, namely control, needs to be explained. The control is effected in 3 directions, namely side to side, as governed by the rudder, up and down, as governed by the elevator, and lateral balance, as governed by the ailerons. And now, with the engine running, the propeller pulling, the wing ready to lift, and the pilot operating the controls, the airplane flies. Now that we have investigated the secret of flight, let us return to aviation's history. The first sustained flight in Europe was made in September 1906 by Alberto Santos-Dumont. The box kite construction of his plane lent a certain amount of lateral stability. Most Europeans doubted reports of successful American flights until a Wright Brothers flight in France finally convinced them. In 1908, then Curtiss advanced America's lead in aviation with a new type of construction which introduced ailerons, or little hinged wings, to control lateral motion. This development eventually replaced the wing warping arrangement of the Wright brothers. The celebrated monoplane Antoinette, developed by Levasseur of France, was one of the first single-winged airplanes, and it proved superior to other designs so far evolved, particularly as a wind fighter. With Levasseur himself swinging the propeller, the Antoinette was first flown by Latham in November 1908. Improvements in design during 1909 brought about increased maneuverability, particularly in the case of the famous Blériot monoplane, which set a high standard of performance. On July 19, 1909, Louis Blériot, designer and pilot of this remarkable little airplane, startled Europe with a flight of 31 miles. Blériot was one of the greatest personalities in the developmental period of heavier-than-air craft. Santos-Dumont successfully completed several short journeys in the famous monoplane Demoiselle. By this time, actual flying competition had begun with a French air meet in August 1909. In October 1910, an American aviation meet took place at St. Louis. Theodore Roosevelt climbed to a precarious perch beside the famous pilot Arch Hoxsey. Colonel Roosevelt's enthusiastic reaction to his flight focused public attention upon the advances made in airplane design and converted many skeptics to interest in aviation. Many novel designs evolved from early European efforts. The gyroplane of Louis Breguet achieved short flights. Louis Paulin's Gypate triplane was surely radical in construction. Somewhat better performance was achieved by the Sloan bicurve and similar attempts to secure more efficient lifting surfaces. 1911 saw the appearance of one of the first passenger transport ships, the Albessard Airbus. This year was also notable for the development in America of Curtiss airplanes designed to take off from water instead of land. Coffin, a well-known pioneer flyer, demonstrated an early Burgess Wright float seaplane in a notable flight which ended in New York Harbor. It was obvious that the ability to operate from both land and water would add to the airplane's usefulness and safety. And so came the development of the early amphibian planes. In the period just before the beginning of the World War, the most efficient and popular airplanes still bore a strong resemblance to the earliest designs. Many famous pilots flew these planes as the use of aircraft became more widespread. Miss Ruth Law and her Curtiss biplane became familiar sights to thousands of enthusiasts in all parts of the United States. With the increasing use of aircraft, and particularly because of the impetus given the industry by the outbreak of the World War, factories began to turn out large numbers of planes on both sides of the Atlantic. By this time, the design aircraft had become fairly well stabilized. More efficient power plants had been developed, and the stability and maneuverability of the average plane was much improved. The harrowing years of the World War brought specialization to airplane design. Civil flying practically ceased while the aviation industry of the warring nations turned attention to the development of many types of military planes. The war accelerated progress in man's conquest of the air, but combat planes possessed qualities far different from those required for civil use. Speed and maneuverability were all important in war aircraft. In 1914, 70 miles per hour was a very good airspeed, but by 1918, an English pursuit plane was doing 160 miles per hour. Monoplanes were almost entirely superseded by biplanes, which were at the time stronger and better fitted strenuous aerobatics. An important development during the last year of the war was the establishment of the first airmail route from New York to Philadelphia and Washington. On May 15, 1918, Lieutenants Webb and Edgerton brought mail through to Washington in a war-type plane. The first of many spectacular transatlantic flights was undertaken in 1919 by 3 United States Navy flying boats designated as the NC Squadron. Leaving North America at Newfoundland on May 16th, they flew toward the Azores. En route, the NC-1 and NC-3 landed to take their bearings and were disabled by the seas. The NC-4 was the only one to reach the Azores by air. After refueling and awaiting better weather, Commander A.C. Reed and his 5 companions took off in the NC-4 for England. On June 14, 1919, John Alcock and A.W. Brown of England made the first non-stop flight across the Atlantic from St. John's, Newfoundland to Clifton, Ireland in about 16 hours. Despite a minor crack-up on landing, the flight won a $50,000 prize offered by the Daily Mail. A short time later, headlines announced the establishment of a passenger service between Paris and London, marking the start of commercial aviation in Europe. In the United States, after several unsuccessful attempts, the first non-stop transcontinental flight began on May 2, 1923. Lieutenants McCready and Kelly of the United States Army Air Service flew the T-2, a modified Fokker transport, from New York to San Diego in 27 hours. Another memorable Air Corps achievement was credited in 1924 to the World Flight Squadron, led by Major Frederick Martin. 4 Douglas planes left Seattle on April 6, 1924. The leading plane cracked up in Alaska, but the flight continued under the leadership of Captain Lowell Smith, and 2 of the original planes finished the historic passage. The first around-the-world flight was completed in an elapsed time of 175 days. A period of experimentation which intervened at this time brought such developments as this flapper plane. By pedaling furiously to gain momentum, the inventor expected to take off with a flapping of wings, but he didn't. A contemporary effort was the cycle plane built by an American idea man. The idea may have been good, but the cycle plane wasn't, so no records were broken. Later came bird-like planes built in a search for greater stability, but few of them were successful. For years, the helicopter was classed with perpetual motion as a physical impossibility. But with propellers mounted to lift the ship vertically, the Terras Pescara of Paris actually made a flight of 20 feet at an altitude of 24 inches. A new era of geographical discovery began with the first great exploration flight of Commander Richard E. Byrd Bennett. Taking off from Kings Bay, Spitsbergen in a Fokker trimotor transport plane on May 9, 1926, these 2 pioneers flew North Pole and back in 15 hours. This was the first important flight through which of heavier-than-air machines in exploration. With the posting of a $25,000 prize for the first non-stop flight between Paris and New York, 2 French aviators, Captains Nunez-Serre and Colly, set out from Paris on May 8, 1927, in an attempt to cross the North Atlantic on a non-stop flight to New York. They had planned to fly a direct course to America, but somewhere en route they met with unforeseen difficulties and vanished forever. May 20th, 1927 is the date of the most romantic adventure in the history of aviation. On this chilly gray morning on Long Island, a young air mail pilot announced his intention to fly to Paris. With his plane groaning under a tremendous load of fuel, he barely cleared power lines at the edge of the field. Charles Lindbergh was on his way to Paris alone. A crowd of thousands surged over the Paris airport at Le Bourget, cheering wildly when they sighted the small silver monoplane. In 33.5 hours, Lindbergh had completed his historic flight of 3,610 miles, and the people of France made him the man of the hour. Upon his return to America, New York gave Lindbergh a welcome that has never been equaled in the history of that enthusiastic city. Lindbergh's trail-breaking flight was followed shortly by eastward crossings by Clarence Chamberlain and Richard E. Byrd and his companions. It was not until 3 years later that a Paris to New York non-stop flight was made. In a Breguet plane on September 1st, 1930, Dieudonné Coste and Maurice Bellant flew to New York in 37 hours and 18 minutes. Amelia Earhart, who had already flown the Atlantic as a passenger, determined to be the first woman to make a solo hop to Europe. On May 20th, 1932, she took off on the Eastward Passage. Flying almost the same course as that taken by Lindbergh, she headed along the shortest path which lies well up in the North Atlantic. But her plans miscarried, and on May 21st, she came down at Londonderry, Ireland, after a flight of 2,026 miles in 15 hours and 18 minutes. An amazing spectacle was the mass flight of 24 military seaplanes from Italy to the United States. Under the command of Italo Balbo, this air armada flew in 7 hops from Orabatello, Italy to Chicago in July 1933. Successfully completing the westward hop, the Italian flyers were received with much acclaim in several American cities before the beginning of their return journey. The round-trip mileage of this great mass flight was about 12,000 miles. Spectacular in 1933, flights of this caliber have since become routine. For example, in July 1939, a crew of 105 officers and men delivered 15 long-range bombers assigned to Hawaiian patrol duty in an uneventful non-stop flight across the Pacific from the Naval Air Base at San Diego. Such flights as this are common and little publicized in America's present-day naval and military aviation. One of the most gallant flights in the annals of aviation took place immediately after Balbo's mass flight from Italy. On July 15, 1933, the American aviator Wiley Post started on a lonely, hazardous solo flight around the world. In 1931, Post had completed a record world flight with Harold Gatty, but this time in the same plane, the famous Lockheed monoplane Winnie Mae, he flew alone. 7 days, 18 hours and 49.5 minutes after his takeoff, Wiley Post completed a 15,600-mile journey, which earned for him a permanent place among aviation's immortals. One of the most significant flights in aviation history is a round-the-world dash made quite recently, July 1938. Howard Hughes, equally well known as a pilot and as a movie producer, decided to make the most complete preparations possible for every stage of the journey. His plane, an especially fitted Lockheed monoplane, was equipped with every known modern instrument for aerial navigation. When the flight was completed in 3 days, 19 hours and 8 minutes, Hughes had conclusively proved the value of adequate preparation, high-grade equipment, and efficient navigation. Operating through such agencies as the National Advisory Committee for Aeronautics, which maintains developmental laboratories at Langley Field, Virginia, science and research continue unceasingly their contributions to safety and efficiency in aircraft design. The development of wind tunnels in which accurate scale models and even full-sized airplanes can be exhaustively tested has accelerated progress in both civil and military aviation. A system of charted light beacons marks the safe path from city to city. And radio communication between plane and ground keeps the flyer in contact with control stations at all times. Under the Civil Aeronautics Authority, a complete system of radio range beacons guides traffic along the commercial highways of the air. And a new and interesting development, the radio landing beam, guides the incoming plane to a safe landing, even when the ground is invisible to the pilot. The source of the landing beam and runway localizer beacons is a small house at the edge of the field. The landing beam is projected upward at a small vertical angle. The true landing path is in the lower half of the beam along the solid line. When the plane about to land reaches the landing path, the horizontal pointer of the instrument, actuated by the landing beam, stands at the central circle. The vertical needle, operated by the runway localizer beacon, gives horizontal guidance and intersects the central circle when the plane is on the true runway course, regardless of its altitude. At an altitude of 1,000 feet, the incoming plane penetrates the landing beam, but it continues past the actual landing path, whereupon the horizontal needle goes up. For above the path, the plane is nearer the core of the beam, where the energy is greater. Seeking his true course, the pilot drops lower. The panel instrument, receiving a weaker impulse from the beam, sends the horizontal needle below the central circle and again indicates an error. The pilot then increases his altitude, finds the true landing path, and follows it unerringly to a safe landing on a surface that may be totally obscured. The many safeguards which science and research have contributed within the past few years have made possible the great network of airlines that serve the people of America today. Carrying passengers, mail and express on regularly scheduled flights between major cities and from coast to coast, the nation's commercial airlines provide speedy transport unrivaled elsewhere on the world's airways. The first airplanes successfully used by United States commercial operators were the Ford and Fokker trimotors, which are already museum pieces. Yet to these sturdy, reliable ships of 10 years ago, we owe much of the success achieved by commercial aviation during its first period of expansion. America's great air transport, with its magnificent equipment, its unrivaled record, and its highly trained personnel, is the backbone of civil aviation in this country. Every member of an airline staff knows his job from start to finish, and a high sense of personal responsibility and teamwork produces typically American efficiency and operating safety. Regulations require the frequent dismantling and overhauling of the powerful engines to eliminate the possibility of mechanical failure. And expert mechanics see to it that no plane leaves the shop until it is in absolutely perfect condition for flight. Servicing operations on the field before departure are completed with equal care. Each man has a specific job to do, and he is proud of his ability to carry out his work to flawless perfection. The brain center of the airport is the control tower, from which all field operations are controlled by radio. When the ship is on the line, passengers and baggage, the powerful radial engines have been warmed up and checked, and they roar their readiness to lift their burden skyward. A salute from the dispatcher gives an okay for the takeoff, and the big plane rolls away. As the ground sinks below, passengers settle down to the pleasant monotony of flight, confident of their security in the cabin of one of America's great airliners. From the ground below, thousands gaze aloft to marvel at the familiar but thrilling sight of the Silver Giant's flight. Even greater things are in store for us as the nation's airlines foster progress. This gigantic transport ship, the Douglas DC-4, was developed at the cost of $1.5 million to fill an order placed by the four major transcontinental operating companies. Thus, greater luxury and speedier and safer aircraft are produced to meet the needs of an air-minded people. The government's program of air preparedness has given great impetus to an already thriving aircraft manufacturing industry in the United States. Civil aviation, too, has increased its demand for more and better planes. Foreign airlines and governments are anxious to buy quantities of American ships, designs of which our aeronautical engineers have already declared antiquated. Everywhere, American engines and airplanes are famous for their efficiency and reliability. So factories in many parts of the country are working day and night, striving to keep up with the demand. But the production of more airplanes is only one phase of the growth of aviation in present-day America. Today, we need more pilots, both for national defense and to man the nation's civil airways. Many young people are discovering the magic of flight by learning to soar in sailplanes or gliders. The modern glider is very similar to power-driven aircraft. There are controls to direct flight, the same as those found in motor-powered planes. There are two simple controls, a rudder bar operated by the pilot's feet and a hand-operated control stick which rises between his knees from the bottom of the cockpit. When moved forward or back, the control stick raises or depresses horizontal tail surfaces called elevators, which control up or down motion of the plane. The foot-operated bar controls the rudder, which steers the ship from side to side, just as a rudder guides a boat through water. Side-to-side motion of the control stick moves hinged panels called ailerons in each wing. When one aileron goes up, the other goes down, thus raising one wing and lowering the other to tilt or bank the plane. By the use of these three control surfaces, the balance of the glider and its motion in the air may be governed by the pilot. The airplane can push or pull itself through the air to create the required relative motion, but a glider must always be falling through the air under the pull of gravity. When a glider hovers in space, goes upward in a climb, it is because the ship is falling gently downward in a quickly rising vertical air current, which rises faster than the glider descends. An expert pilot knows from applicants for advanced training. In schools and colleges throughout the United States, aviation classes have been established with the cooperation of the federal government. Young people everywhere are enthusiastically adopting wings, and a new and greater generation of flyers is already beginning to emerge. The Army's Eagles earn their wings at the world's finest flying schools. This is Randolph Field in Texas, where the pick of America's young manhood arrives at the gateway to adventure. Their first lesson is to learn the military bearing required of a soldier. 2 weeks of preliminary training in school, where he learns the principles of aerodynamics, and an Army pilot is rated at the peak of his profession, and he must learn many things before he graduates. Communication, both in the air and on the ground, is vital to efficient operation of the Air Corps. So the fledgling must learn the radio code so that he may receive and transmit messages while in flight. 6 to 10 hours of dual instruction and many hours of solo flight are required before the student is ready to go up with the dawn patrol for practice at the art of aerobatics. In his lab, cadet is taught how to handle his plane under every possible condition. Mass flights from point to point, cross-country flights, formation flying, and navigation at night are all part of the curriculum. During the 12 short months of the course at Randolph Field, the cadet receives the most comprehensive training in all branches of aviation. During training, pilots learn to fly blind in a miniature plane equipped with all controls found in a regulation plane. An instructor transmits simulated radio beacon signals while maneuvers are recorded by a machine which traces the course on a map. The flying standards of the Air Corps are the highest in the world, and when the cadet finally graduates, he receives an Army commission and becomes eligible for a commercial pilot's license. He has mastered the machinery of flight, and he has learned to use the amazing instruments which have been developed to increase efficiency and safety in the air. Whether at the controls of a giant transport or in the cockpit of a flying fortress, the new pilot is ready to do his part to maintain America's supremacy in the air. Within the short space of 10 years, United States Airlines have hurdled the Atlantic and the Pacific, carrying both mail and passengers on regularly scheduled flights between 5 continents. Though gallant and ambitious attempts have been made by other nations to challenge our position in transoceanic transport, these efforts have so far produced no serious rivalry. Gigantic seaplanes like Germany's famous Do X have been built and flown across the seas, but the factors of safety and reliability characteristic of American transport planes have always been lacking. The product of endless research, fine craftsmanship, and great engineering ability is today's American transport. This is the China Clipper, trailblazer of the broad Pacific. A larger version of the same general design is the famous Yankee Clipper, which carries passengers and mail on regularly scheduled flights non-stop to Europe. Literally a boat with wings, this giant sea transport has a massive boat-like hull to support its 41¼ tons of weight on the water. 4 1,500 horsepower engines provide power to lift the streamlined mass and propel it through space at 200 miles per hour. Inside the Yankee Clipper are complete, luxurious living accommodations for 32 passengers and a crew of 8. Even later design is this 50,000-pound flying boat built for long-range passenger service. 22 feet from top to keel, she has 2 decks of passenger compartments within her massive hull, and built into the wings are 2 engines which are miracles of power and dependability. 4,000 thundering horsepower send the big ship skyward to take her place on the highways of air commerce. From drawing boards, wind tunnels, and laboratories come other new designs to challenge the outermost limits of earthly space. Sealed against the cold and the rarefied air of high altitudes, powered for swift flight in the lonely vastness of the substratosphere, this is evidence of the unswerving ambition, the high courage with which man pursues his skyward course. Let us look backward in memory over the span of less than 40 years to man's first feeble but successful attempts to fly. Let us never forget the faith and courage of those early pioneers of flight, for their achievements freed man forever from the bonds that held him earthbound. We have come far since the Wright brothers first challenged space in the year 1980. And as we enter the 5th decade of the 20th century, we turn toward the future with the question, where now? What conquests lie ahead?